So as an example of this last case that I said, let's go back to free energy. Now the non-interacting electron gas that we can of course calculate in a simple way, and we did calculate this in a simple way. We're just summing all energies up to the Fermi level. But we also looked at this from the functional integral method, and we found that the free energy here was the expression I already had written down in the beginning. So we had the sum here over from Matsubara frequencies and the summation of our momentum, and what we sum is the log. And here I now introduce this symbol psi p, which is just the energy of the non-interacting electrons measured from the Fermi level. Okay? This notation I will use. So we have here we encounter a situation where indeed the function that we sum doesn't have simple poles but has a cut. Okay? So let's look at the corresponding Matsubara sum. So using the Matsubara summation technique, you can write the sum of this S again, log minus so this temperature factor here always also appeared, and this nicely cancels for the feeder, which enters in the definition of the Counting function. So we can write this just using the technique introduced as an integral over contour gamma 1, and I will make a picture again, where here now I use the Fermi distribution function, and then we have the counting function is the Fermi distribution function. We have here this function where omega n is substituted by minus iz, so this gives a minus z plus this. So here we had a minus t, the t is cancelled by the beta in the counting function, and the minus is cancelled by the pole of this Fermi distribution. Okay, so this is why we have 1 over 2 pi I. So this is what we arrive at, and let me just once draw the situation here that we now encounter. So we have again a complex plane where we have the imaginary part of Z and we have the real part of Z. We have the fermionic Matsubaras, and we start off from this contour here. Which is contour gamma 1. Okay? So that's the starting point in this integral. So now we have to carefully look into this function here, and we can define the cut of the log at the negative values. So whenever z exceeds this value psi p, which is fixed, in the end we have to sum over p, but here it's now fixed. When this exceeds this, we enter the cut. Okay? So we have here somewhere the value psi p, and here we have the cut of the logarithm. Okay. So, but still we can use this formalism now, which is now a little bit, let's say, more complicated in the way that now, if we deform this contour, we have to be careful here. So what we end up with is, again, this inflated circle, but then we remain with a contour which, like if we take this and just pull this around this cut, we will have an integral along this contour. Okay? So this would be an integral over the real axis a little bit shifted below. So let's call this epsilon minus, a little bit below the real axis, so this would be a definition of epsilon minus some I0, and 0 we send to, can think of some very small element, and this would be the contour shifted a little bit into the positive, so this would be epsilon plus I0. Okay? So if we then form this contour, we should integrate then here along this function here. Okay? So now what we can do to simplify this is that the function that we integrate doesn't have any problems for values epsilon, let's say, smaller than psi p. Okay? So we can just, if we like, to simplify the expression, we can then deform this contour, which was this was closed here. We can just, for simplicity, extend this to minus infinity, because here the two contributions from this integral and this integral, they just annihilate themselves, because here we can just close this. Okay? So this is equivalent because we don't have any singularities here. Okay? So we can write this integral then in the following form. We can write this as an integral over 2 pi I. Now we have an integral over d epsilon from minus infinity to infinity. So as said, in the beginning we started from integral from psi p, and then we should add this little curve here, but we can just use this to extend this to minus infinity. That doesn't make any problem. And then we have well, the Fermi distribution function, beta epsilon plus 1. And we have the log of beta minus epsilon plus psi p. Okay, so this would be the integral on this contour, and then the integral on this contour just has the opposite direction, so it comes with a minus, and then what changes is only the sign in the epsilon. So we can write this in the same integral here and just subtract this here, okay? Ln beta minus epsilon minus plus. And make a big bracket here. Okay, so this first contribution is just this integral up here. The second contribution here with this is the integral down here, which differs by the sign due to the different orientation, and the epsilon plus changed to epsilon minus. Okay, I hope you can read this. Okay. So now what we can still do is we can realize that this Fermi distribution function we can write as a derivative with respect to the energy epsilon of log 1 plus epsilon minus beta epsilon. Okay. So if you take the derivative with a minus, you get 1 of minus, and you get an epsilon to the minus in the numerator, so you can write this as an epsilon plus, and then if you make the sides right, you get a minus t here. Okay, you can see that this equals this expression here, and then we can look at this integrand that we have here. Okay, so what do we have? We have that this function for epsilon going to infinity, this becomes just a 1, the log of 1 vanishes. Okay, so this function here closes, makes this integrand vanish at 0, epsilon going to infinity, this is 0, while this function, well, as said, we've extended it to minus infinity, but just because here the two contributions cancel. So this integrand here just vanishes at epsilon minus to infinity. So this means that here now we can do the partial integration, okay, because this is all well behaved. Make the partial integration, then we have the log here. This derivative will give us two fractions. Okay, so let me write down what you get after partial integration. So we get a 2 I, then we have the integral from minus infinity to the infinity, the epsilon. So here we did the partial integration, so this remains log. And then here from the derivative we get an epsilon plus minus c pi minus epsilon epsilon minus. Okay. So this is after partial integration using, I mean, that we saw that the boundaries will contribute, and now we can see that this here is just of the form epsilon plus, or let's call it z plus I0 minus z minus I0, okay? And in the limit where, well, this 0 goes to 0, this is just giving you a delta function, yeah? So this gives you I pi delta of z, probably use a minus, minus pi delta z, okay? So this here will just, will give us wait, this is the imaginary part of this one, so this some the imaginary part of 1 over x plus I0 gives you the minus pi delta x. So this here will come with a minus 2 pi I, okay? Delta this. So this is a minus 2 pi I delta. Okay, so this is the identity, so the imaginary part still has 1 over 2i, which you multiply here, so the minus pi becomes 2i. So then, I mean, the integral of epsilon is just very simply done, so minus 2 pi I into 2i hence, so we get a minus t, and then we get the log of epsilon minus b. Okay, so this is the result, and actually if we now put this into the free energy, well, then of course we get what you already know, we remain with the sum over p, and then we have the log of the 1 plus e to the minus b. Then now I put in the, sorry, c pi, I put again the c pi, which was p squared over 2m minus mu, and log this here. Okay, this is of course what we know. Okay, so this is in a way, in a more complicated way, deriving something that you already know, I mean, from statistical physics or whatever, but once you see how you derive this from the Matsubara field integral. Okay. So that was the example for a more complicated thing where you have a cut, and actually it's a good exercise if you do this once for the bosons. Yeah, so another good exercise. And so here, I mean, one had to be a little bit careful to like make it the right way. That I mean, here we use the partial integration doesn't get any contribution from the boundary. So I mean, there was some freedom. We could have here defined omega n to minus omega n. Okay, so there's some. You have to make it the way that it works out. And if you go through this one Poland, you will see this. Okay, questions or so that's I think I mean the most I mean the cases that you will encounter are single singularities or this kind of cuts where you just integrate over then integral contours shifted slightly above and below. Okay, you see that naturally then always the distribution functions pop up, and I will make another exercise sheet with quite a lot of examples of this, because this again one has to do a couple of times, and this is just things that always will pop up in the Matsubara field integral. Okay? was the technical part, and now we can just go back to the original problem of the free energy of the weakly interacting electron gas. And okay, so let me just go back to our problem that we had and what we've done so far. So it was the free energy of weakly interacting electron gas. So what we did is we calculated the free energy of the non-interacting electron gas, and we saw that this is natural to measure this in units of the Rydberg energy, and then found that this is proportional to n, and then we had this dimensionless parameter Rs, which told us if we are in the weak or the strongly interacting case, and this Rs is related to the density, so at large densities we are in the weakly interacting case. And then we have calculated the free energy contribution from the first order perturbation theory, and found that this is a correction in 1 over Rs, which now is smaller in 1 over Rs, okay? So we see already that this really appears as Rs appears as our physical parameter that we suspected. It means we have the large density limit, and we calculated this from looking at two diagrams, which was the Fock diagram, and then we had the Hartree diagram, which we said was just in this case 0 due to the charge neutrality, so we have here a closed loop, so there's no momentum exchange, and V of Q equals 0 was just 0 because of the homogeneity of the whole system. Okay, so this is what we encountered from doing perturbation theory. Now what I just want to mention is actually if you look at this expression more precisely that you get from the first order perturbation theory, you already see that there's some problem popping up. And so I want to explain what is the problem, and then I want to give a hint why you should also expect that there is a problem appearing in first order perturbation theory, that this is some problematic result. And already you can already understand like what will cure these problems is going to higher orders perturbation theory. So this is kind of motivation why later on we look at higher orders and actually will full, summation of some subclass of diagrams infinite order perturbation theory. So let's first look at this more carefully, at these two contributions from the non-interacting and the first order perturbation theory, to see that there is something going on that is not okay. Let's think what the reason for this might be. Let's take a second glance at this. So if we take the analytical expressions that we wrote down for the free energy, then in the zero temperature limited, we can write this in the following way. So the zero temperature limit, the Fermi distributions appearing everywhere just become theta functions. So we sum here over momentum smaller than Fermi momentum, the 2 is due to spin summation. Then we have the p squared over 2m from the non-interacting electron contribution, and the first order correction from perturbation theory we could include in the following way, or we can include in the following way. Okay, so we saw that or actually we didn't see, but this is also probably an exercise. So we wrote down the first correction to the free energy. We saw that this is a double sum over two products of Green's functions over P and P prime in Matsubara summation. So if you do the Matsubara summations, I gave the result, then you had a product of two Fermi distributions at epsilon P prime, multiplied with the potential evaluated at P minus P prime. Okay, so this is actually the result of the Matsubara frequency summation. You can see, I mean, the Green's functions just have simple poles, so you can see that the product of GP prime, that just becomes the Fermi distribution of epsilon P and Fermi distribution of epsilon P prime. It's just exactly one of the simple examples, so this is probably one of the exercises. So you already wrote down, and then in the zero temperature limit, the product of the two Fermi distribution becomes two summations where P and P prime are in absolute value smaller than PF, and what you sum is just the matrix element of the interaction. Okay, so you can rewrite this sum in this form, and this now has a nice interpretation because you can understand this just as sum over momentum smaller than P Fermi, and what we sum is some renormalized single particle energy. Okay, so you can understand this here as a renormalization of the single particle energy due to the interactions. Okay, well, let's call this renormalized single particle energy, and taking into account only first order interaction process. Okay, so let's take a closer look at this renormalized energy. So a calculation, which I also leave as an exercise, of this energy shows that this can be written in the sum, well, of the non-interacting part, and then first order interaction, so it's proportional to E squared, and it's PF times over 2 pi sum times a function which depends on the absolute value of the momentum measured in units of the Fermi moment. Okay, this function gamma has the following form. So gamma of x is 2 plus 1 minus x squared over x ln 1 plus x divided by 1. Okay, so this is the result of doing this integration here. So we can try to do it. It's, I think, also in Mahan and other books, but yeah, you can try to do it. If maybe make also an exercise out of it. But you can just believe me that, well, one can do this integral here, and what one arrives at is this function here. Okay. Now, if you look at this function shown here, one encounters the following. So this is as a function of x, gamma, we plot it as 1. Looks like, let's say, as this form, but there's some important thing of this function, which you can see that this function here has a logger divergent derivative at the value at the value 1. Okay, so this you can just confirm by taking derivatives. So you find some problem in the derivatives, some divergency at the value x equals to 1. Now x equals to 1, this is measured in units of the Fermi momentum. This means there is some divergency of this derivative at the Fermi momentum. Now this means that the derivative of the single particle energy has a divergency at the Fermi momentum. And this actually doesn't make a lot of sense, as can be illustrated, for example, at the density of states. So this, first of all, has unphysical implications. Illustrated as a single particle density of states. So let me just recall what the density of states is. So the density of states per volume is factor 2 is due to spins. Per volume is just the summation over the single particle spectrum of all states, and what you sum is a delta function at the single particle spectrum, okay? And well, you can write this, transform this into an integral for pi. And volume factor cancels this out. P. So this is in 3 dimensions, p squared delta epsilon minus epsilon p. So this is standard thing. And then what you find here is this is p epsilon divided by p squared. And here you get the derivative, the inverse derivative of single particle spectrum. And this p epsilon is just from inverting or expressing the energy in terms of momentum. Okay, so if you have like a quadratic spectrum, this p epsilon is just 2m e square root. Okay, just to keep it general, so I just brought them. Okay, so you start from the delta function. You can convert the integral, the sum into an integral. So this will give you a factor L over 2 pi to the cube. Okay, so this is here. Then you do the integral over the angular part. This gives you the factor 4 pi. And then this derivative here can be, well, you can convert the integral just into an energy integral. And this then will give you, converting the momentum into energy will give you just the Jacobian, so the inverse of this derivative, and this is now evaluated at the energy epsilon. Okay? So the message here is, if you look at the single particle density of states and an energy epsilon, this is proportional to the derivative of the spectrum divided by p. The derivative of the spectrum with respect to p, and this is the inverse, okay? 1 over the single particle, the derivative of the energy. Okay, so now what we said is that this function here is logarithmically divergent, has a logarithmically divergent derivative, okay? So this means that the energy, so single particle energy here has a logarithmically divergent derivative at the Fermi momentum. So if we take this here, the inverses mean that this just vanishes at the Fermi momentum. Okay? So if you would take this divergence serious, this would mean that the single particle density of states would just vanish at the Fermi momentum. Okay? So if you take this here, then this would imply that the single particle density of states at the Fermi momentum is 0. But we know, that all the transport properties are just determined by the densities of state at the Fermi energy. So these would all vanish, okay? And this doesn't make any sense. Okay, so there's some problem in this result that we encountered here. Okay? Let me just write down this here. So this would mean that actually all transport coefficients, activity and so on, would vanish due to weak interactions, and this doesn't really make sense. Okay? So now if you look at this and try to trace down the problem where this comes from, well, you can see that this comes from the function here, okay? So the log appearing here, which gives the problem, just comes from the integral of 1 over q or 1 over p. Okay, so if you use the two-function integral. So you can trace back this problem here due to the 1 over p or 1 over q interaction between the electrons. Now, this means the 1 over q, I mean, it's just it's just a Fourier transform. Actually, it should be p squared, no? It's just a Fourier transform of the Coulomb potential, the long-range Coulomb potential. Okay. So we can see that the problems that we find here are all due to the long-range nature of the Coulomb interaction between the electrons. But then we have to recall, well, what we did so far is just look at first-order perturbation theory between the electrons. Now, these electrons are not just in vacuum, no? It's not just there's one electron and another electron and they interact with each other, but they are electrons in a matter. So they are electrons where you have, like, you draw the Fermi sea, can take some electron excitation, some hole, and they interact with each other. But now these particles are in some medium which is just consists of the fermions, the electrons of the Fermi sea. And this medium is polarizable, no? So typically what will happen is that the other electrons which are still in the Fermi sea, which in this interaction process we just looked at two particles and said they just interact and all the rest doesn't do anything. That's not true. I mean, there's all the other electrons around. We have a finite density, actually a high density, and all the other electrons will react also to any potential by screening it. No? So this is polarizable. So what will happen is, for example, you have here just created a hole in the Fermi sea. There should be electrons in the vicinity here rearranging to screen this charge. Okay? And this means that actually the interaction in this polarizable medium shouldn't be the bare interaction, but there's some screening going on. And this screening is definitely beyond what we considered here, because we just said, let's take two particles, charged particles, look at their interaction and see what this gives. But we should go to higher orders to say, well, there's more interactions because there's screening going on in the Fermi sea. So we see that the first order result actually gives some problem, which we can relate to the log, which is due to the long-range nature, but which is an artifact of just considering first order. If we go to higher orders, we should expect that there's something more interesting going on, and hopefully this will cure this. So this is why we should definitely look at the higher orders and see how this, I mean, will change the results. Okay, so this is like the motivation why, or one of the motivations why it should be interesting to go to higher orders to see what is going on. So let me just write this down here. So this is some problematic result, but you can somehow see where this comes from. Well, let me first write down here. The problem is the renormalized single particle energy, I mean renormalization due to first order. This can be traced back to the long range interactions, meaning going as 1 over q squared, or it's equivalent to 1 over r of Coulomb interaction potential. Action okay, so this was this here, it's this. And then you notice that however the electron gas at large densities has mobile charge carriers, so they can just rearrange however they like. Carriers, and if they are mobile, then they will tend to screen interactions. But this is surely an effect which is beyond first order perturbation theory. In first order perturbation theory as interaction, and yeah, then probably we'll just go to the higher orders next week. No, on Wednesday. Yeah. Okay, so maybe who's motivated and has some time can just like, so we said that we can calculate the free energy perturbatively by just looking at the expanding the partition function and just looking into taking into account the connected diagrams. So whoever is motivated can till Wednesday just go to second order and we just look at these two. This is second order perturbation theory, in the interaction. So now the statement is to calculate the free energy in second order. One just has to look at all connected diagrams that can be formed out of these two interaction vertices. So whoever likes can just maybe try to figure out what are the diagrams in second order for the free energy. Okay. I think I want this.